So in this lecture we're going to learn how to solve another class of first order ODEs, which would be in general different than linear and separable equations that we already know how to solve. And to understand the procedure, let's look at the following function y of x that is defined implicitly. Right, so remember, if I give you an equation, if it is solved for y, then the function is defined explicitly. If it is not solved for y, but yet it relates y and x, like what you see here, then the function y of x is defined implicitly. Of course, in this case, it's easy to find the explicit solution. Explicit expression, just solve for y, and you'll see that there are two functions in this case. Once you take a square root, there are two functions, y equal to plus something and y equal to minus something, both of which actually satisfy this implicit equation. What I want to do is I want to determine what sort of ODE would this implicitly defined function satisfy, and I want to figure out the ODE by taking an implicit derivative. So how do we take implicit derivative of y with respect to x? Basically, we assume that y here is a function of x, and then we take derivative of both sides of this equation. Right side is equal to the left side, so the derivatives must be the same, and then use a chain rule on the left-hand side. So take a derivative with respect to x on the left equal to the derivative of with respect to x on the right. On the right you have 1, derivative of 1 is 0. And the chain rule on the left says that the derivative of y squared should be 2y times y prime. And the derivative of x cubed minus x is simply 3x squared minus 1. And so then, as you have already seen before, if I want to figure out what y prime is, I simply have to solve this equation for dy dx, and I get derivative in terms of x and y, because my original function was given to me implicitly. But not, on the other hand, this equation that I see here is an equation that involves x, y, and y prime. So by itself, this equation that I denoted by star is an ODE. That's an ODE which is a form 2y prime plus 3x squared equal to minus 1. All right, so then what I basically discovered is that my original function, implicitly defined function y squared plus x cubed minus x equal to 1, is a solution of this ODE. Okay, so whatever, right, that's fine. I can also notice here that the same equation actually is separable. So if I take the equation when it is written in this form, I can separate variables like this. And so the equation is separable, so I can solve it as such. But I don't want to do it in this section. I want to figure out a different way of finding the solution. What I want to observe first is that if I go back to my original implicitly defined function, and if I replace 1 by any other constant, 2, 7, minus 50, any constant, c, then when I take an implicit derivative of the equation, at the end of the day, I'll end up taking derivative with respect to x of a constant, which will be 0. So that means that it doesn't matter what the constant is on the right side. Once I took the derivative, then I'll always get the same equation like this. Which means that the left-hand side equal to c will form a one-parameter family of solutions to this equation. And that one-parameter family of solutions is what I would expect, because equation is the first order, so it requires one integration, so there should be one generic undetermined parameter. So then what we conclude is that this expression should be a general solution, so this one-parameter family of solutions, which encodes all of the solutions to the ODE. So this is a general solution of my ODE. Okay, so starting from the solution, I got the equation, and then I know that what the general solution of that equation is. Okay, fine. So can we reproduce the same procedure for a more general case? Instead of giving you a precise version of my implicit function, I'm simply going to assume that I have y defined implicitly via some function of x and y equal to a constant, right? That's basically the same story as what I have here, except that in this example, my f of xy was a function that I chose to be something, some particular choice. I use some particular choice of the function. So now I'm trying to do the same thing generically without specifying what capital F is. So what kind of equation ODE will be satisfied by this implicitly defined function? Well, I do exactly the same thing as I did above. I know that some y of x that I don't really have an explicit expression for right now, that the function y of x solves this equation for any x, which means that I can take derivative of both sides of this equation with respect to x, because both right side and left side now depend on x. On the right, because I have c, derivative of c is 0, so that's easy. And on the left, I have capital F, which depends on x in two different ways. It depends on x directly. It also depends on x through y. And you might recall the multidimensional chain rule for functions of many variables, which told you that the way to take a derivative of this function with respect to x, what you have to do is to take a derivative with respect to x directly first, and then the derivative with respect to y, and multiply that by derivative with respect to x. So if there is no dependence on x, if f is a function of capital Y only, then this is just the usual chain rule, which I'm going to list here, but because of many variables, you also have to add partial of f with respect to x. We discussed that, well, you discussed that in Calc 3. So by taking the derivative of capital F equal to c with respect to x, I come up with this equation. So this is a first order differential equation, right? Because it involves the first derivative of y with respect to x. And any ODE in this form, it has a name, it's called an exact equation. So your equation is going to be exact whenever it has this form. Partial of some function with respect to y times derivative of y with respect to x plus partial of f with respect to x. Similar to what we did before for when we separated variables, I can rewrite this by using a slightly different notation. I can multiply both sides of this equation by dx, and then the equation is written in a differential form, but it is otherwise exactly the same equation as before. So to summarize what we just discovered is this, that if I take my exact differential equation in this form or that form, then I know that my regionally chosen implicitly defined function f of x y equal to c, that function will be a solution of this ODE, right? So in this case, I kind of don't need to solve the ODE because I started with the function and then I determined the ODE which that function satisfied. So that means that once I see an equation in this form, then I know that its solution is going to be that function capital F that appears in the equation equal to a constant. Okay, so now let's suppose that I have an equation which has a form like this, except that I don't know if multiply these functions by which I'm multiplying dy and dx. That's what I don't know in advance, that they are actually partials of the same function with respect to y and x. So we have an equation like this, which is a more general version of an equation here, right? Because p and q can be any functions and not necessarily partials of the same given function capital F. So by looking at the equation like this, because I don't know if the function capital F exists for which P and Q are partials, I need to determine if P and Q are actually partials of some function. And in order to accomplish this, what you do is this. We first make the following observation. Let's suppose that this is true, that this equation is exact, and P is a partial of some f with respect to x, and Q is a partial of the same f with respect to y. So then what do we know? What we can do is this. We can take partial of P with respect to y. If we do that, then that's a partial with respect to y of df dx, which is a second partial derivative of f with respect to dx first and then dy. If q is df dy, then if we take derivative of q with respect to x, it is going to be this, and that's a second partial of f with respect to y first and then with respect to x. Now here I'm not paying I'm not looking at the minute details of mathematics of this. So let me just say that we know that as long as we're dealing with continuous functions here, as long as the derivatives are appropriately continuous, then what should be true is that if I take a second partial of f with respect to x and then with respect to y, or vice versa, I should come up with the same result. So that means that since two partials are exactly the same, then dp dy must be the same as dq dx. And for our purposes, for the purposes of functions that we consider in this class, because mostly we're dealing with functions that are continuous, but you just have to be aware that there might be situations when things are not going to work. So, but for us, most of the time, the reverse of the statement is going to be true. So here I assume that P and Q are partials, and then that means that dp dy is equal to dq dx, right? So if P and Q are partials of the same f. So the reverse is also true. If you have functions P and Q that are sufficiently nice, and you take dp dy, and it is equal to dq dx, then it turns out that there exists a function capital F for which P is df dx and Q is df dy. So the moral of the story is this, that if I have the ODE P dx plus Q dy equal to 0, then this ODE is going to be exact as long as partial of P with respect to y is equal to the partial of Q with respect to x. So that's how you test if the ODE that you got is actually exact. So let's do an example. Let's say I have an equation x squared dx plus cosine y dy equal to 0. I want to verify if it is exact or not, like I said, and then if it is exact, I want to find the general solution of this equation. That is something that we have not discussed yet, but basically I have to integrate this equation. So you will see in a second what that means. Okay, so if P is x squared, then the partial derivative of P with respect to y that I need to take, I'm taking partial with respect to y holding x fixed. There is no y in P, so derivative must be 0. Likewise, Q depends on y only, so if I take derivative of Q with respect to x, I'm holding y constant, so that derivative is 0. So then both dp dy and dq dx are 0, and so dp dy is the same as dq dx, so the ODE is exact. Now, what does it mean that the ODE is exact? Now, moving on to trying to solve it. It means that there exists a function capital F for which P is going to be its partial with respect to x, and for which Q is going to be its partial with respect to y. So I'm looking for capital F because P is x squared and Q is cosine y. I'm looking for function f such that partial of f with respect to x is x squared, and partial of f with respect to y is cosine y. Well, so if I know the derivative of something, then how do I recover that something? I need to integrate. So for instance, I know that partial of f with respect to x is x squared. So if I fix y and I take the derivative of capital F with respect to x, I get x squared. How will I undo it? I still hold y fixed, and I will integrate x squared with respect to x. So capital F must be an integral of df dx with respect to x by holding y while you're holding y fixed. So p is x squared, or df dx is p is x squared. So we need to take an integral of x squared with respect to x, easy. This is just x cubed over 3. And in principle, you have to add c. Well, so you add c, but remember that in this case, you're holding y constant. So that means that c in principle can depend on y, because if y is a constant, then c prime of y derivative of that with respect to x is going to be 0. But then that means that I found my function capital F, but it still contains an unknown function c of y in it that I still have to determine. Well, but so far I only used information about the partial of f with respect to x. I'm still supposed to use the information about partial of f with respect to y. And here is how I'm going to use it. So I just figured out that capital F is x cubed over 3 plus c of y. So if I take this capital F and I take its partial derivative with respect to y, this must be the same as cosine y that I already know. So let's take partial of f with respect of this f with respect to y, holding x fixed, then x cubed over 3 is a constant, and we just get c prime of y. But again, df dy, on the other hand, is equal to cosine of y, or q. So that means that c prime of y must be equal to cosine of y. So if c prime of y is cosine of y, notice that here I don't have any x left, right? The left side depends on y and the right side depends on y. This is a consequence of the fact that the equation is exact. If somehow you did not check that the equation is exact, and it isn't, at this stage you will see something where maybe the right hand side depends on x, but the left hand side doesn't, which is not allowed. But anyhow, so if c prime of y is cosine of y, then c of y is antiderivative of that, and derivative of cosine is sine. So c of y is equal to sine of y in principle plus a constant, but I'm not going to write a constant here, and it will be clear why in a second. Okay, so then I take this c of y that I found, and I substitute this c of y into the expression for capital F, and I end up with this. And then we discussed earlier that the solution of my exact equation is going to be the function capital F, general solution is going to be function capital F of xy equal to a constant. So in this case, if this is my function capital F of xy, then a solution of this ODE is going to be the thing in the box, capital F of xy is equal to a constant. And just one point here, so again, I said that I'm not going to add a constant to this when I'm integrating for the second time. And indeed, you can see that if I did, then I'll have the expression on the left plus unknown constant equal to another unknown constant. So then I can move the first unknown constant on the right, and then just combine them, and I simply get an unknown constant. All right. So a couple more points here. What if I have a separable equation, right? So the way I'm writing exact equation kind of resembles the way we wrote a separable equation. If I have a separable equation, then it should have a form like this. Then I can separate variables, and I end up with an equation like that. And I compare it to my exact equation. So if I interpret this as an exact equation, I can think of f of x as p of xy. I can think of minus 1 over g of y as q of xy. And if I take dp dy and dq dx, I will see that I get zeros for both of those. So that means that for any separable equation, dp dy is equal to dq dx. So any separable equation is also an exact equation automatically, right? Because dp dy is equal to dq dx. The reverse of this is not going to be true, as we will see in the example that I'm going to do now. So let's do this example. So I have an equation like this, and the question is whether or not this equation is exact. Well, first of all, per what I just said, this equation is not separable, right? Because I cannot take e to the y plus 3x and write it as a product of x and y. I will not be able to put all x's on one side and all y's on another side. So this is genuinely not a separable equation, but hopefully so I cannot solve it as a separable equation, but possibly I can solve it as an exact equation, if it is. Okay, so then what is p in this case? P is a thing which multiplies dx, x minus 3y. Q is a thing that multiplies dy. Notice an important thing here, that my exact equation looked like p dx plus q dy. So q should incorporate whatever sign, both p and q should incorporate whatever signs are sitting in front of these expressions. So q is minus e to the y plus 3x. Okay, so verifying if the equation is exact or not, I take dp dy, I get minus 3, I take dq dx, holding y fixed, e to the y goes away, so again I get minus 3. So dp dy is dq dx, and the equation is exact. Because it is exact, there exists a function capital F, such that df dx is p and df dy is q. And so in the previous example, I took df dx and I integrated it with respect to x to recover f. Here I'm going to go in the opposite direction. I'm going to take df dy, which is a partial of f with respect to y, holding x fixed. I'm going to reverse this operation. So to get capital F, I'll integrate df dy while holding x fixed. Now, who is df dy? It's q. Who is q? It's this expression up here. So I need to integrate this with respect to y holding x fixed. Integral of the minus exponential is again minus exponential, right? Because I can keep minus sign outside. And integral of 3x, x is a constant. So integral of 3x must be 3xy, and we get 3xy. And because I'm integrating with respect to y by holding x fixed, I should be able to add a constant which depends on x. And so now to figure out the unknown function c of x, follow the same procedure as before. Take that function that you just found, take its derivative with respect to x, and if I take the derivative with respect to x, it will be this thing holding y constant. Derivative of e to the y is gone, derivative of minus 3xy is going to be minus 3y, and then c prime of x. And I know that df dx is supposed to be also equal to x minus 3y, so what I found, df dx must be the same as x minus 3y. Similar to what I discussed above, so now if I compare the left side that is circled to the right side, minus 3y appears in both, so I can cancel it out. And what I have left is c prime of x is equal to x. Again, as a consequence of the fact that the equation is exact, all dependence on y here is gone. Well, and if c prime of x is x, then integrating x, I get x squared over 2. Once again, I'm not adding any constants at this stage. And so then my capital F is this guy with c equal to x squared over 2. So you get that expression. And so the general solution of the ODE is going to be this capital F that I found. General solution is take that function and set it equal to c. And once again, the solution is going to be a function prescribed in an implicit form. In this case, in fact, I will not be able to solve it for y because of the presence of exponential. But I can write this as a function x of y by solving a quadratic equation. But really, I don't have to do that because I'm not being asked to produce an explicit solution of my ODE, but implicit. And that I found already. And now let's just quickly use this to solve an initial value problem. So same equation, but now I'm going to supplement it by an initial condition, y of 0 is equal to 1. So I already have a general solution. I just need to substitute the initial data into that solution to figure out what c is. So I have to substitute x equal to 0 and y equal to 1. And if I do that, then I'll recover that c is equal to minus c. And therefore, replacing c by minus c, I get a solution to the initial value problem, and that is written down here. So in the next lecture, we're going to do more examples of this.